Welcome. This is a time series analysis course. My name is Nicoleta Serban. I'm an associate professor in the Stewart School of Industrial and System Engineering. This lecture is on modeling heteroskedacity. And in this lesson, I will introduce the concept of non-constant variance or heteroskedacity. First, we'll learn about the difference between conditional and unconditional variance. Given a time series, the conditional variance of the time series at time t is the variance of the time series given the past values of the time series. In contrast, the unconditional variance of the time series at time t is simply its variance disregarding the past data. We commonly refer to conditional variance as volatility. In the simple case when the time series data are independent, that is, what happens at current time t does not depend on what happened in the past, then the conditional variance is the same as the unconditional variance, since the variability at time t is independent of the variability of the past data. Independence implies lack of dependence or lack of correlation. On the other hand, in the case when the time series data are uncorrelated but not independent, then we have that the covariance between any two variables in a time series is zero, meaning that there is a linear dependence between any pairs of the variables in a time series. However, it is possible to find a transformation f of the variables in a time series such that f of x1, f of x2 to f of xn are in fact correlated. That is, a non-linear dependence. One common transformation we'll use in this course is the power transformation. For example, square power transformation. Under uncorrelated data but not independent, we do not have that the conditional variance is equal to the unconditional variance. How can we diagnose independence and uncorrelated but dependent data? We have independence when the ACF plot of the time series as well transformations of the time series resemble the ACF of white noise. On the other hand, we have uncorrelated data but still dependent if the ACF plot of the time series resembles that of white noise, but the ACF plot of a transformation of time series does not. The difference between independent and uncorrelated data becomes apparent when we study the residuals from an ARMA model applied to data with non-constant conditional variance. We'll see in some illustrative data examples that while the residuals are white noise, the squared residuals may not be white noise. ARMA models are used to model the conditional expectation of a process given the past data. But in an ARMA model, the conditional variance given the past data is assumed constant. The class of heteroskedastic models is a generalization of the models so far through relaxing the assumption of constant conditional variance of the time series and therefore modeling nonlinear time series. What does this mean for, say, modeling stock returns? For example, suppose we have noticed that recently daily returns have been unusually volatile. We might expect that tomorrow's return is also more variable than usual. However, an ARMA model cannot capture this type of behavior because its conditional variance is constant. So we need different time series models if we want to model the non-constant variance or volatility. We need to consider more general models in which both the conditional expectation and the conditional variance depend on past time series data. To be more specific, if we begin with an ARMA model as provided on the slide, the residual process ZT which is assumed to be white noise with constant variance given by sigma squared, this will be an ARMA model. However, in many applications, Time series data often exhibit volatility clustering, where time series show periods of high volatility and periods of low volatility indicating non-constant variance. If that's the case, we can rewrite the error term sigma t as the product between a deterministic but time-varying component sigma t and a random process RT with mean 0 and variance 1. In the formulation provided in the previous slide, sigma t is of interest as it models the conditional variance of the time series. Sigma t is often referred to in financial literature as volatility. What are the important features of sigma t? The function sigma t may be high for certain time periods and low for other periods, also reflecting clusters of variability. The function sigma t varies with time in a continuous manner. In other words, there are no discontinuities, anomalies in the volatility. The function sigma t varies within a specific range. That means is not infinite. It takes a finite range of values. The function sigma t commonly is assumed to have the so-called leverage property. In other words, it reacts differently to large amplitude changes from the small amplitude changes in the time process. A straightforward approach to estimate the conditional variance is using non-parametric regression. Specifically, after applying a time series model for the conditional expectation, for example, a RIMA model, we approximate ZT by the residuals of the model. Further, we can take the log of the squared residuals under the model specified in the previous slide. Log of the squared ZT is equal to log of the conditional variance plus an error term epsilon t, which is log of squared RT. We can then use non-parametric regression on the log of squared residuals to estimate log of the conditional variance, or log of sigma t squared. To obtain the estimate of the conditional variance, we can transform back by taking the expectation, by taking the exponential of the estimate of the log sigma squared t. This approach can provide a good estimate of the conditional variance if it changes smoothly over time. For modeling more complex structures in volatility, other models can be considered as introduced in this lecture. Modeling heteroskedacity has become important in the analysis of time series data, particularly in financial and economic applications. These models are especially useful when the goal of the study is to analyze and forecast volatility. If we can effectively forecast volatility, then we'll be able to price, for example, more accurately, create more sophisticated risk management tools, or come up with new strategies that take advantage of the volatility. Classic applications in finance where the estimation of volatility is needed is, for example, for option pricing, specifically in the Black-Scholes model for option pricing, which is dependent upon the volatility of the underlying financial instrument. It also can be needed in tradable securities where volatility can be traded directly by the introduction of the CBOE Volatility Index, abbreviated VIX. To be even more specific, in financial data, it is very difficult to predict the mean of the price of a financial instrument, such as stock price. If it were to be easy, other investors would predict the price as well and trade in such a way as to remove the advantage of the prediction. As a result, due to the removal of the predictable information from the financial instrument by investors, almost all that is left is a random walk with a weak trend. The long-term growth rate reflects how to trade the financial instrument. If it has large volatility in the future, the returns need to be larger to attract investment to compensate for the risk of a loss, of a potential loss. Other applications are of estimation volatility or the conditional variance. Variance are in the risk management, where volatility is a direct measure of risk in management and investment. More generally, volatility is a measure of uncertainty in any decision making. Similar principles as in investments for financial instruments apply within other settings where risk of uncertainty plays an important role in decision making. In summary, in this lesson, I introduced the concept of non-constant variability in time series, or so-called heteroskedacity. Thank you. Welcome. This is a time series analysis course. My name is Nicoleta Serban. I'm Associate Professor in the Stewart School of Industry and System Engineering. This lecture is on modeling heteroskedacity, and in this lesson I'll illustrate a concept, a non-constant variance or heteroskedacity, with a data example. To simulate the time series with a time series with non-constant conditional variance in R, we need to perform a simulation approach as for the random walk simulation. That is, we need to simulate a vector W for the random white noise, then a different vector called here EPS for our time series values, and finally a vector sigma SQ in this simulation for the conditional variance. The coefficient A0 and A1 are to capture MA effects and B0 to capture AR effects in the conditional variance as provided in the formula for sigma squared, the conditional variance. The last two R commands are for plotting the ACF for the time series as well as for the squared time series. This simulation model is described here. The time series is epsilon t. The sigma t is the standard deviation of the conditional or the square root of the conditional variance. The ACF plot of the time series is in the upper panel, and the ACF plot of the squared time series is in the lower plot. While the ACF plot of the time series resembles that of white noise, the ACF plot of the squared time series does not. We see that the first three legs are outside of the confidence band, indicating zero correlation in a squared time series. This is an example of uncorrelated data, but not independent, since the squared time series is correlated data. We'll consider one data example of a financial instrument, the stock price of a company. I selected here a company with very large volatility, BDCA Energy, which is a crude oil and natural gas producer with headquarters in Denver, Colorado. Daily stock price for more than 10 years of data starting with January 2007 are considered in this data example. The reason for being interested in assessing volatility for this company is because it is highly dependent on the crude oil price. For this analysis, I'm using R functions in the quant mode package for R, which is designed to assist the quantitative traders in the development, testing, and deployment of statistically based trading models. Using the R command get symbols is possible to load data from a variety of sources, including Yahoo Finance, Federal Reserve Bank, Google Finance, and this data could include stock price and other financial instruments. In this implementation, the source is Google, and our command for plotting the time series used from this package is candle chart. The time series plot is here. The time series is clearly non-stationary with a non-linear trend. But how about the volatility? It seems that there are periods of high volatility. A better way to visualize volatility is by plotting the return of the log price. And here's a time series of the return time series. This time series clearly shows large volatility in the first quarter of 2008, for example. This time series indicates that we have non-constant conditional variance. We'll first fit an ARMA model. For this, we'll select the order of ARIMA, including the order of ARMA and the order of the integrated part of the model. The code provided here is slightly different than the one we used in fitting an ARIMA model, because here we're only interested to select the order without saving the AIC values. We begin with 0 orders, then search for P and Q orders between 0 and 10. For the difference order, we select between 0 or 1. We fit the ARIMA for all combinations of orders and update the final.order and final.ARIMA fit until the AIC value does not improve or does not reduce anymore. The selected orders are P or AR order equal to 5 and Q or MA order equal to 6. The selected order for the difference of the time series is 0. Last, we obtain the residuals for the final model. The residual plots are here. The ACA plot of the residuals looks like one for the white noise process. On the other hand, the ACF plot of the squared residuals suggests that there is a serial dependence in the squared residuals. Thus, the residuals are linearly uncorrelated, but not independent, since the transform residuals, specifically the squared residuals, are correlated. Let's test whether the residuals and squared residuals are correlated using hypothesis testing. We apply here the box-Lewin test. Note that the test is not for testing independence, but for testing whether the data are uncorrelated, where the null hypothesis is that the data are uncorrelated versus the alternative that the data are correlated. Based on this test, the p-value for testing uncorrelated squared residuals is very small, indicating that we reject the null hypothesis and thus conclude that the squared residuals are correlated. The p-value for testing whether the residuals are uncorrelated is also small, suggesting that an ARIMA model, the ARIMA model does not lead to uncorrelated residuals for this particular example. Last, we estimate the variance using non-parametric regression. As presented in the previous lesson, we take the log of squared residuals and apply non-parametric regression approach. We can apply the splines regression model using the GAM function in the MGCV library of R. In this implementation, the response is the log of squared residuals. Here I'm replacing the closed price in the PDC price object with the square root of the exponential of the fitted values in order to maintain the same data structure. Next, I plotted the fitted volatility. The plot of the fitted volatility is here. We can see that indeed the volatility has a nonlinear trend with 3 years of high volatility. To see whether I captured the high volatility periods using this estimation approach, I'm contrasting here the estimated volatility with the time series of the return log price. But by contrasting these two plots, we clearly see that the periods during which we estimate high peaks in the volatility correspond to years of high variability in the return price. In summary, in this lesson, I illustrated the concept of non-constant variability or heteroskedacity with specific data examples. Thank you.